Alright, so part 2 of our parent functions. The next function we're going to look at is the square root function, and this is over on the wall. You can see it. It is f of x equals the square root of x. Now, the thing about square root functions is we're not going to be dealing with any negative x values. All of our x values are going to be positives. So when I choose the values for my my little table here, I want to choose values that I can take the square root of. So what is a value I can take the square root of, a small number?
4.
4. Alright, so I'm actually going to put 4 right here. What's lower than 4 but you can still take the square root of it? No. 1. What's lower than 1 but you can still take the square root of it and it's not negative?
0.
0. So the square root of 0 is 0. The square root of 1 is 1. And the square root of 4 is 2. So when I graph this, I'm going to have 0, 0, 1, 1, and 4, 2. Notice that this thing is curving and it's rising ever so slowly. It's not rising quickly at all. It's going to take forever for it to get higher and higher. Now, it's going to get big quick with the x values, but with the y values, it's not going to get big quick at all. Okay? Think about it. The square root of 100 is what? 10. So you could go out 100 places and you're only going to be up 10 places. But it's still rising up. It's just very slow. So the domain for this is not all real numbers, because where does the x value start? 0. So bracket 0 to infinity. Where does the y value start? 0. Bracket 0 to infinity. Now, no, it's positive. It's going up. Oh, no, well, the only way it could be negative infinity is if it's reflected. If there's a negative out front of this, then it would be reflected down and it would be negative infinity.
What if it's going to the left?
It can't go to the left because you can never have x values. It can only go to the right or be flipped under and still go to the right. Okay, so what would the reflection look like? The reflection would just simply be, you would take, where's my thing? You would take that same drawing and just kind of flip it under, and it would look something like this. Okay, but there's still no negative x values. There are some negative y values, but no negative x values.
Because 0, 0.
Exactly. Well, because you can't take the square root of a negative number. It wouldn't make sense for this. All right. Now, we can take square roots of negatives in the complex number system. We'll get there later, but not for the real numbers. All right. X-intercept. Where is it? 0. Y-intercept is 0. Maximum number of roots are zeros. 1. And this is why. If I shift this thing down, it's still only going to cross the x-axis one time. There's no way I can get it to cross more than once. Alright, end behavior. As x goes to what? What does it end? 0. So, really, it ends at 0. It's an endpoint. So, as x goes to 0, y also goes to 0. When it comes to end behavior, if there's ever a point on the end, then whatever coordinates of that point are, in this case 0 and 0, that's your x and y. Now on the right side, it's an arrowhead. So as x goes to infinity, what does y do?
Go to infinity.
Goes to infinity, just goes very slowly. But if it's going to infinity, does it really matter how fast you're going if you just keep going forever? I mean, not really. Just not going to go as far as fast. Alright. But you'll eventually see everything. Well, actually, you won't ever see everything because it's infinity.
Oh, this is.
Because you keep going. Alright, this isn't physics class. Alright. Is this continuous? Yes. The graph itself is continuous. Once you start that graph, there are no breaks in that graph.
No going back.
So it is continuous. Alright. Cube root. The cube root is similar to the cubic function. It's just like the inverse of it. So it's f of x equals the cube root of 3, cube root of x. Now, again, I need to do my chart for this, and I'm going to use 5 points because I want you to see how it works. What's that? What? Because it wasn't supposed to be a 3, it's supposed to be an x. I messed up. Alright, so the cube root of x. So I'm going to do 5 little places on my table. 1, 2, 3, 4, 5. Alright, and again, I'm going to start with 0 in the middle. And then I'm going to carefully choose values. I'm not just going to go up by 1 or down by 1 or whatever. The cube root of -1 is okay. I can do that. I can also do the cube root of -8. I can do the cube root of 1 and the cube root of 8. And so the cube root of -8 is -2. It's like the backwards of the cubic function, right? -1, cube root of -1 is -1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. Now remember, cube root is, you're looking for the value that you can multiply by itself 3 times to get the number underneath the radical. So 2 times 2 times 2 is 8. That's why the cube root of 8 is 2. Everybody good with that? Alright, now when we graph this -8 here is going to be off the chart a little bit, but I'm going to try to put it close to where it would be. So this would be 6, 7, 8, and then down 2. So it would be right in here. Alright, and then -1, -1, 0, 0, 1, 1, and then 8, 2. So 6, 7, 8, 2. So it looks like the cubic function, but it has been turned sideways. Now, when we talk about how many maximum x-intercepts there are, or the maximum number of roots or zeros, there's only going to be one of those. Because if I were to kind of do what I did with the cubic function and make it cross 3 times, it wouldn't be crossing the x-axis 3 times, it'd be crossing the y-axis 3 times. So it could look like this. It could do this, okay? But this is 1, 2, 3 on the y-axis, but only 1 time on the x-axis. So it's going to be maximum of 1. Alright, so the domain, from -infinity to infinity. The range, -infinity to infinity. The x-intercept, 0. The y-intercept, 0 for this graph. The end behavior, very similar to what we've seen before. As x goes to -infinity, what does y do? Goes down, right? To -infinity. As x goes to positive infinity, y goes to positive infinity. It's going up. Slowly, very slowly, but it's still going up. And it is continuous. All it is that cubic function turned sideways. Okay, it's actually reflected and turned sideways.
Oh, this one is going to be on this.
Yeah, it is. Alright, the next one's reciprocal. You can see it over there. It is also called rational. So write down rational underneath that. Okay, I would rather use the terminology rational function because rational means fraction, right? So this is just a fractional function. It's a function that involves a fraction where the x is in the denominator. And it is f of x equals 1 over x. That is the most basic rational function. Now, later this year, we will learn specifically how to graph rational functions. And there are several things that go into it, but there's several easy steps to do it. No matter really what the rational function is, we can do it pretty simply. Alright, now the domain is going to be, I'm just going to sketch this, and you can see what it looks like over there on the wall, but I'm not going to do a table because I just want to sketch it. I want you to understand, and this is not a great drawing, that these curves will approach the x-axis and the y-axis forever, but they will never touch it. They're going to get closer to it, but they're never going to touch it. I'll fill that in just a second. Yeah. All right, so what that means is that there's a break. The breaks are called asymptotes. What are the asymptotes? The x-axis and the y-axis are your asymptotes. So what are our asymptotes? X equals 0. That is the vertical, and that's really the y-axis. And then y equals 0, and that's horizontal, and that's really the x-axis.
So the flip opposite.
Kinda. So, the asymptotes are the equations x equals 0, that's a vertical line, and y equals 0, that's a horizontal line. Those represent the axes. It is discontinuous because the asymptotes are lines that the graph gets closer to but can never touch. Think about an electric fence. You don't want to touch it. You can get close as you want, but if you touch it, you're going to get shocked. So these lines are like electric fences. Don't get close. You can get close to it, just don't touch it. All right. Now, because of that, our end behavior is going to look a little, I'm going to work backwards this time. Our end behavior looks a little different because of these asymptotes. As the x goes to negative infinity, it's getting closer to the x-axis, but is it ever touching the x-axis? So what is the y value of the x-axis? No, of the x-axis, what is the y value? 0. So it's getting closer to 0, but it's just never touching it. It's approaching it. That's what this arrow means. It approaches 0. So as x goes to the left, it's actually going up slowly, but it's never going to actually touch the 0. It's just going to get closer to it. All right, on the right side, as x goes to positive infinity, it also gets closer to 0. The y goes down towards 0. So that's a little different. All right, maximum number of roots or zeros. Now, this one, the parent doesn't have any roots or zeros. All right? It doesn't have any roots or zeros because it doesn't ever cross the x-axis. But could I shift this thing down? Could I shift like where the asymptote was like here at -1 instead of here at 0? Yeah, I could. Then how many times is it going to cross? 1 time. If I shifted it up like 1 unit, how many times would this bottom part cross? 1 time. So what's the maximum number of times? 1. Okay, again, there is no x-intercept and y-intercept for the parent. Okay, the domain is going to have a break in it. It's going to go from negative infinity to 0, but you need to use parentheses because it's not including it, union 0 to infinity. And the range is going to look just like that. So how would we write the range? So there we go. We went backwards. It's a different function, different type of function compared to the other things that we've seen.
Coach, would you put 0 on the x and y intercepts or just NA because it actually doesn't?
Well, yeah, that should be none. Thank you, Ms. Willis. That is exactly right. I almost did that in my first class too, then I caught myself. So it's not 0, because 0 is a number, right? It's none. Thank you so much for that. All right.
You get a discontinuous function, will you always have a union?
Yes.
Okay.
You sure will. When you're doing, it may not always be, it may be for, it could be discontinuous for one and not the other, if that makes sense. There are some functions that look like this. Like if this is my grid, it might look like this, where you come down this way, and it's like that, and then this one, let's see how I want to do it, kind of like this, okay? But notice how this value is lower than, this curve is lower than this curve. So vertically, I'm doing all the y values, but horizontally, I'm not doing all the x values. So there are some functions that look like that, some rational functions, so it's not always going to be where both parts are discontinuous. The graph will be discontinuous, but your range might be from negative infinity to infinity, whereas the domain might have a union. That was a very good question. All right, exponential. Last two things here, exponential. All right, exponential functions, you can see it on the wall over there. There are two types of exponential functions. There is your growth and your decay. Generally speaking, the function is f of x equals a times b to the x. Now, the a and the b have special meanings. The a is what would determine the stretch or shrink of this function. We'll get into all that later. The b value, b for base, that's going to determine whether it's growth or decay. So, if your b is greater than 1, then it's growth. Write this down. b greater than 1, growth. If b is between 0 and 1, this means 0 is less than b is less than 1. That means b is in between 0 and 1. It's not negative necessarily. It's just in between. The a value could be negative, but the b value is not negative. That's going to be decay.
It's 0.
0, less than b, less than 1. Alright, I'm going to graph the decay and the growth on the same grid using two different colors. You may not have two colors.
Just put like A or B.
Alright, now in finance, if something is growing or you're making money, that you would generally use black. You say you're in the black, okay, and your checkbook is in the black, that means you've got money in your checking account. If your checkbook is in the red, then you don't have money in your checking account, okay? So I'm going to use black and red. Black would be growth, red would be decay. Alright, so when I graph these things, I'm not going to graph it perfectly, but the asymptote for these functions is going to be the x-axis for your parent exponential functions. So I'm going to draw that with a, let's see here, just brown. Okay, so the asymptote is the x-axis. That asymptote can shift. We can shift these things all around. It can shift it up or down. We'll learn that later. All right, so for the growth, we're going to have a y-intercept of 1. It's going to go up to the right. Now, this is not a perfect graph, but it's just the sketch. When we do graphs of these, we just do sketches. All right? So, this is your y-intercept. Notice it's going down toward the x-axis forever, but it's never going to touch it. It's going up forever. That is your growth. All right? Now for the decay. The decay is also going to have a y-intercept of 1, but it's going to go down. It's going to go down to the right instead of up to the right. And it's never going to touch that asymptote. It's going to get close to it, but it's never going to touch it. So if we're graphing these in the future and you cross the asymptote, then I have to take points off. If your arrowhead crosses it, like just the little arrowhead part, I don't take points off. You have to understand that with exponential functions, you don't cross the asymptote. You can't. Alright, so the red is decay. So these are two different types of exponential functions. You're not going to graph two different types on the same grid. Okay, you're only going to graph one. Alright, so over here, I'm only going to do the characteristics of growth. So make a note that this is only growth. because I don't have room for both of them. This is the growth. Alright, so what is the domain and range of growth? Domain is from negative infinity to infinity. The range is from 0 with a parentheses to infinity. It's actually the same for decay. So the growth and decay, domain and range, exactly the same. Alright, x-intercept, none. Y-intercept, 1. I'm sorry, I should say none. Yep. Alright, none for the x-intercept, 1 for the y-intercept. Okay, it's the same for growth and decay. Maximum number of roots or zeros. It has none in this state, but if I shift it down, how many could it have? 1. Maximum of 1. Okay, now the end behavior is going to be different for growth or decay, so I need to make another note. We're talking about growth here. As x goes to negative infinity, then what is the y value doing in the black here?
Right.
It's going toward what? 0. Alright? In the positive direction, as x goes to positive infinity, what is the y value doing? To infinity. Alright? And is this continuous? Yes. There's no breaks. There's not a part of this graph below and above this asymptote. It's just all above. It's just continuous. Alright, the asymptotes. For this parent function, the asymptote is the x-axis, which has the equation y equals 0. Because remember, horizontal lines are always y equals. Alright, last one. Logarithmic. Logarithmic functions and exponential functions are inverses. In other words, they undo each other. Just like inverse operations, division will undo multiplication. Addition will undo subtraction. Square rooting will undo squaring. Cube rooting will undo cubing. Logarithms will undo exponential functions. Exponential functions will undo logarithmic functions. So they are inverses. This is the function. F of x equals log base b of x. Now, we'll learn all this stuff later. The point is not to know how to do logarithms right now. The point of this is to just simply know what the graph looks like. That's it. Alright, so our exponential function had an asymptote. It was the x-axis. Guess what this asymptote is going to be? Y-axis. Which is the equation x equals 0. So I'm going to put a dotted line here.
On 0?
Mm-hmm. Alright. Now, that's my asymptote. Okay, the graph is going to have a x-intercept of 1. And it's going to do... Make sure I do it right. It's going to do this. Okay? Notice how the graph looks kind of like the exponential function, but it's approaching the y-axis, but it's never getting there. So working backwards, it is continuous. As x goes to 0, the y value goes to negative infinity. As x goes to infinity, because it goes to the right forever, the y value goes to infinity. The maximum number of roots or zeros is 1. The x-intercept is 1 for this problem. The y-intercept is none. The domain goes from 0 with a parentheses to infinity, and the range goes from negative infinity to infinity. Because it goes down forever and up forever. Alright, so that's it. So I'm going to stop the video.